contextualize late interaction over BERT. So in this video, we are going to discuss about what exactly is ColBERT, what are late interaction models, and what are multi-vector models. And to be honest, these three are exactly the same. So late interaction models are also called multi-vector models because they create a lot of vectors. And ColBERT is the exact model name, and these two are the model family name, like a category name. So late interaction models and multi-vector models is a category, and ColBERT is one model of that category. There are other models as well, which is ColBERT V2 and late on, which is the latest model. Then we'll talk about ColBERT versus normal embedding model versus cross-encoder models. What are the differences between the working of those? How exactly they work? What are the pros and cons of those? Exactly, as I said. And then we'll see when to use which family of model. And at the end, I have prepared a benchmarking Python notebook in which we'll compare the recall versus latency number, like in real, with the dataset called SciFact, BEIR, Benchmark Information Retrieval Dataset. I'm using that dataset. On that dataset, I ran the benchmark and I'm comparing different models here. So one model from normal Bi-Encoder family, one model from Cross-Encoders, and two models from late interaction ones. One is ColBERT V2 and one is the latest one, which is called Late On. There's a company called Light On. They have launched this model recently and it's a little bit better than ColBERT V2 and we'll see how much. So in case of late interaction models, we create one vector for each token. So if you see on the right side here, there is normal embedding model and we create like a one embedding for this whole document. Assuming you are creating embedding of this whole document at once, you will create it. Of course, in RAG we do chunking, and if you do like a per paragraph chunking, like one paragraph will have one vector or one embedding. But let's assume this whole thing is your chunk. So in normal embedding model case, you do insert this whole paragraph or this whole page into the model. It will give you only one vector, which is of a certain dimension. It can be 768 or 1536. But in case of late interaction model, which is ColBERT, what we do, we take vector embedding of each token, not a paragraph, not a page, nothing like that. We take like one token by token. And here I'm assuming like one token is one word, which can or cannot be the case depending upon the text, as you know. So this is the whole thing actually, that one token, one vector, not whole page and one vector. And in this way, the model is able to capture lot more semantic meaning of each token, and that is the whole idea behind late interaction models, that it captures token by token, and that's why the model is able to capture the semantic meaning in a much better way. But there is one more layer, that your query token and document token interact at a very late end in the process. So we'll see that next. So I'll quickly show you. Let's assume you have this document. LLMs predict the next word. So here, let's assume this one sentence is the document, not the whole page, just for the simplicity, for the explanation. And your user is asking the query how LLM works. So we create, again, for the query as well, we create one vector for each token, how one vector, LLM one vector, work one vector, and similarly for document as well. And what we do, we calculate the dot product of query vector for each token with each token of the document as well. So if you see how will be compared with LLM, how will be compared with predicts, how will be compared with the, and will store this dot product values here like this. Similarly with LLM, similarly with work. And then what we'll do, we'll take for each query token, we will take the maximum dot product value, which is let's say zero point 0.2 here. So I'll take that. Then I'll take which is the maximum value from this row, which is 1, and which is the maximum value from this row, which is 0.43. And we'll put it here and we'll sum it. And that whole sum is called MaxSim. And this MaxSim number is basically the similarity between document 1 and your query. And we do this with all the documents in your database. And that's why it is a little bit computationally expensive as well. But the good thing is that you can pre-compute all the embeddings of document, and at the query time you don't have to run this embedding, which is the case in cross-encoder models. So quickly I want to highlight these points, that late interaction models are bi-encoder models only. So just to be very clear here, that late interaction model is also kind of a subset of bi-encoder model, because bi-encoder model, and I'll just go here quickly. So in case of bi-encoder model, we call it bi-encoder because we do document embedding and query embedding separately. That's like twice encoding is happening, one for query and one for document, and that's why it's called bi-encoder. In case of late interaction model as well, we do like a embedding of a query separately and document separately, and that's why it is also a bi-encoder model. The only difference here is that the interaction between query embedding and document embedding happen late in the process, and that's why it's late interaction model. Next point is document token embeddings are pre-computed and indexed offline, which is not the case in cross-encoder, and that's the main problem, because if you do embedding at the query time, it will take a lot of time. So this is also an important highlight of the late interaction models. And the third one is number of document vectors can be different from query vectors, but it does not matter for MaxSim. So as we have seen here, the document tokens are 1, 2, 3, 4, 5, and the query is 1, 2, 3. So document 1 and document 2 might have like only one token, or document 5 have 1000 token. It does not matter because we are seeing this document from the perspective of query, and we are calculating the maxim. So it does not matter how many tokens a document have. One is take the dot product between query and document vector. So generally we do uh, like when we compare the query token vector with document token vector, we take a dot product here, which I just mentioned. And the last point is we take maximum score corresponding to each query token, not the document token. So if you see here, we are taking the maximum score corresponding to this query token. We are not taking the maximum score from this column and this column and this column. We are taking the maximum score from the rows, because query token vector is compared with or being dot producted with each document token vector. That's why it is from query perspective. Basically, we are not going to take maximum of the column, because if you see in this column, we have not taken any score into the mix of maxim. So that is how the late interaction model works. I just want to quickly show you the bi-encoders as well. So in case of bi-encoders, we take the document, and this whole document we calculate the embedding, and there's only one vector here. This is just one vector. Same for query, just one vector. And then at the end we do the dot product or cosine similarity, whatever we think is suitable. In this process, because of this whole compression of these many words, let's say this is one page and I'm just creating one embedding vector out of this whole page, the semantic meaning capturing is not very efficient, which is not the case in multi-vector model, because they create a token by token vectors. I think I'm repeating myself too much. And in case of cross-encoder, it's a completely separate thing. You pass query and document at once in the model, and then inside the model it do self-attention over the joint query and the document and give you the relevance score. So this is how the difference between late interaction bi-encoder models and cross-encoder models. And if you want to know more detail about bi-encoder and cross-encoder, you can watch my video. I have created a detailed video about that. So very quickly, we'll talk about accuracy. So in terms of accuracy, so let's assume accuracy on top is positive, and speed on the right side is like higher speed, lower latency. So late interaction models sit somewhere here. They are quite accurate as well, not as accurate as cross encoders. And when I say accurate, I am talking about recall numbers here, and they are faster as well, because you pre-compute the document embeddings, unlike cross encoder models. Now we'll see what are the pros and cons of each. So let's take bi-encoder. They are the fastest because just one vector, you can use ANN, and you can just quickly calculate the query and compare it with all the documents in your vector database. So it's fast, it's suitable for billion scale, it's low storage because less number of vectors are created, and it is ANN index friendly. Cons: lossy single vector. As I said, it generally does not able to capture complete semantic meaning of the whole document, and that's why it's also weak on rare terms. When to use it? It should be used as a first stage retrieval at scale. So if you have a lot of documents, you can use it as a first stage retrieval, and later you can add cross encoder or late interaction model for re-ranking. So let's talk about cross encoder. They are the highest accuracy and full query doc attention. So as we just saw in the previous diagram, that query and document is passed into the embedding model at once, and there is a self attention happening over the joint query and doc, and that is why the accuracy is highest among all three. If I go to the cons, no pre-compute, documents are not pre-computed. That's why it's very slow, because at query time you have to compute the query and the document encoding at once, and which is a very time consuming process. That's why it's very slow at scale. You cannot even think of using cross-encoder model on a large data sets. And when to use it? So this is generally used for re-ranking for top 100 or 1000 items which you have retrieved using bi-encoders in first stage. Now I will talk about late interaction models. So they are very near accuracy to cross encoders. The good thing is doc side pre-computable, because you can pre-compute the embeddings of document and save into any vector database, and there is a token level matching, so it works best with rare terms. The cons are there's a high storage per token, because every token is being converted into vector, so there is an explosion of vector happening here, and heavier query to compute, because let's say your query is of 10 tokens and your document is of 1000 token, so every query token vector will be compared with every document token vector, and it will be like a lot of combination. So it's a very compute heavy operation. When to use it? You can use it for re-ranking, and you can use it in case where precision is absolutely critical for you. Medical domain or a finance domain, you're building some application where precision is of utmost important to you, you can use late interaction models. So now we are here in the Python notebook, and we'll compare bi-encoder versus cross-encoder versus late interaction models. So here in case of late interaction model, I am using GTE modern ColBERT V1 and the newer model which is late on. And for bi-encoder, let me show you which model I'm using. So this is a setup. I'm using the dataset called SciFact. That dataset is, so this is the dataset. This is a part of BEIR. This is quite well-known dataset for information retrieval benchmarking. So I'm using that. I'm using 300 queries out of it for the testing. This is the evaluation code. I'm not going much into the code because you can ask Claude and it should be able to make you this. I'll just jump into the numbers, and here are the numbers. So bi-encoder model, let me just quickly show you the bi-encoder model name which I'm using. For bi-encoder models, I'm using all mini LM L6v2, and for cross encoders, I'm using this model MS Marco Mini LM L6v2. And for late interaction models, one model is this one and another one is late on this one. And now we'll see the benchmarks. Let me zoom in. So if you see, recall at 10 for bi-encoder is 0.783. For cross encoders, it's much higher, 0.822. And late interaction models, it's higher than cross encoders, which is 0.83, which is not generally the case. Sometimes cross encoder model generally can be more accurate in terms of recall, and late on is much higher than if you compare with bi-encoder. Similar case with precision as well, 0.092, 0.094, and 0.096. If you look at latency numbers, bi-encoders are the fastest. Cross encoder, it took 496 milliseconds. It's crazy high number. You cannot use this in production. Late interaction model, however, is a little bit more digestible here, 17 millisecond and 15 millisecond with reasonable amount of accuracy. So if we compare with bi-encoder and use it as a 0% like a benchmark, cross encoder have plus 5% increase in recall, late interaction model 7%, and late on latest model from the family of late interaction we have 8.5%. Slowdown is 52% almost here as compared to bi-encoder, and this is 1.6 times slower than bi-encoder. So I think this is a pretty good model here. This is all from this video. I hope you found this video helpful. If you want to know about cross encoder versus bi-encoder, you can watch my other video. I have also created a video about HNSW algorithm. You can watch that. Thank you so much.